Today's challenge asks us to determine if a given list of numbers is monotonic. Take a moment. If you were given a list of numbers, how would you figure out if it follows a consistent trend? Let's dive into what a monotonic array actually means. Imagine you have a list of numbers, like a sequence of temperatures recorded throughout a day. A list is considered monotonic if it's either entirely non-decreasing or entirely non-increasing. What does that mean? Non-decreasing means that as you move through the list from left to right, each number you encounter is either greater than or equal to the previous number. It never goes down. For example, the list 1, 2, 2, 3 is non-decreasing. 1 is less than 2, 2 is equal to 2, and 2 is less than 3. This fits the pattern. On the other hand, non-increasing means that each number you encounter is either less than or equal to the previous number. It never goes up. For instance, the list 5, 4, 4, 1 is non-increasing. 5 is greater than 4, 4 is equal to 4, and 4 is greater than 1. This also fits. The tricky part is that a list can be either non-decreasing asterisk or non-increasing to be considered monotonic. It doesn't have to be both, just one or the other. If a list does neither, if it goes up and then down or down and then up, then it's not monotonic. For example, the list 1, 3, 2 is not monotonic. It goes up from 1 to 3, then down from 3 to 2. That breaks both rules. Our goal is to write a program that takes a list of numbers as input and tells us, with a simple true or false, whether that list is monotonic. The list of numbers can be quite long, up to 100,000 numbers, so our solution needs to be efficient. Each number in the list will be within a typical integer range. The main challenge here is figuring out how to check for both conditions, non-decreasing and non-increasing, without doing a lot of redundant work, especially for very long lists. The most straightforward, or brute force, way to approach this problem is to check for each of the two conditions separately. First, we could assume the entire list is non-decreasing and then go through every single pair of numbers to see if this assumption holds. What this means is, we'd pick the first number, then compare it to the second, third, fourth, and all subsequent numbers. If we ever find a number that is smaller than our current number, we know it's not non-decreasing, and we can stop checking that condition. Then, we do the exact same thing for the non-increasing condition. We'd assume the list is non-increasing and again, compare every number to every subsequent number. If we ever find a number that is larger than our current number, we know it's not non-increasing. If after checking all pairs for non-decreasing, we found it was asterisk non-decreasing, then our answer is true. If not, we then move on to check all pairs for non-increasing. If that turns out to be true, then our answer is true. If neither condition is met, then the answer is false. This approach works, but it's slow. Why? Because for a list of n numbers, checking every number against every other asterisk number involves roughly n times n comparisons. If you have 10 numbers, that's about 100 comparisons. If you have 1,000 numbers, that's about 1,000,000 comparisons. This n-squared relationship for time complexity means it gets very slow, very quickly, as the list grows. For space complexity, meaning how much extra memory we use, this approach is very good, only using a tiny, constant amount of memory, regardless of how big the input list is, because we're just comparing numbers in place. The key insight to optimize this problem is that we don't need to check every pair of numbers. We only need to compare adjacent numbers. If a list is truly non-decreasing, then every single pair of adjacent numbers must follow the rule. The current number must be less than or equal to the next number. If even one adjacent pair breaks this rule, the entire list is not non-decreasing. The same logic applies to non-increasing. This is like checking a line of dominoes. If you want to know if they're all standing in a sequence where each one is taller than or equal to the last, you only need to check each domino against the very next one in line. You don't need to check the first domino against the 10th. So we can keep track of two possibilities. Is it still possible that the array is non-decreasing? And is it still possible that the array is non-increasing? We'll start by assuming both are true. We'll declare a variable called increasing and set it to true, and another variable called decreasing and set it to true. Then we'll go through the list, starting from the second number, because we always need to compare a number to the one asterisk before asterisk it. So we'll loop from the second number all the way to the end of the list. Inside this loop, for each number we'll compare it to the number just before it. If we find that the current number is greater than the previous number, it means the list cannot asterisk be non-increasing. So we set our decreasing variable to false. If we find that the current number is less than the previous number, it means the list cannot asterisk be non-decreasing. So we set our increasing variable to false. We continue this process for every adjacent pair. By the time we finish going through the entire list, if our increasing variable is still true, it means the list was indeed non-decreasing. Or if our decreasing variable is still true, it means the list was indeed non-increasing. If either one of these is true, then the entire list is monotonic. So our final answer will be true if increasing is true, or if decreasing is true. This approach is much faster because we only go through the list once. We do a constant number of operations for each number, making it very efficient. Let's trace this optimal algorithm with our example input list, 1, 2, 2, 3. Our list nums contains the values 1, 2, 2, 3. We start by declaring our two Boolean variables. Increasing is initially true and decreasing is initially true. Now we begin our loop. Our loop starts from the second element, so our index I begins at 1. At this point, I is 1. We compare nums at index I, which is nums at index 1 whose value is 2, with nums at index I minus 1, which is nums at index 0 whose value is 1. Is nums at I greater than nums at I minus 1? Is 2 greater than 1? Yes, it is. Since it is, we know the list cannot be strictly non-increasing, so we set decreasing to false. Our variables are now increasing is true and decreasing is false. Next we check, is nums at I less than nums at I minus 1? Is 2 less than 1? No, it is not, so increasing remains true. The loop continues. Now I becomes 2. We compare nums at index 2 whose value is 2 with nums at index 1 whose value is 2. Is nums at I greater than nums at I minus 1? Is 2 greater than 2? No, it is not. Decreasing remains false. Next is nums at I less than nums at I minus 1. Is 2 less than 2? No, it is not. Increasing remains true. Our variables are still. Increasing is true and decreasing is false. The loop continues. Now I becomes 3. We compare nums at index 3 whose value is 3 with nums at index 2 whose value is 2. Is nums at I greater than nums at I minus 1? Is 3 greater than 2? Yes, it is. Since it is, decreasing remains false. Next is nums at I less than nums at I minus 1. Is 3 less than 2? No, it is not. Increasing remains true. Our variables are still. Increasing is true and decreasing is false. The loop has finished as I has reached the end of the array. Finally, we return the result of increasing or decreasing. Since increasing is true and decreasing is false, true or false evaluates to true, so we return true. And there's our final result, true. The algorithm correctly identifies that the input array 1, 2, 2, 3 is monotonic because it is non-decreasing. You'll spot this pattern when you need to check if an entire array or list satisfies a condition based on adjacent elements. If the problem asks whether a list is sorted, ordered, or follows a trend, especially with non-decreasing or non-increasing rules, think about this single-pass comparison of neighbors. The time complexity is big O of n because we iterate through the list once. The space complexity is big O of 1, constant time, because we only use a few fixed variables. Try the next problem in the array category to practice this pattern. Don't forget to like and subscribe for more DSA explanations.